And should be recording, I think. I hope. Okay. I wanted to start by actually looking at a couple of things that are earlier in the chapter on capacitance, because there's a homework question involving one of them, particularly well, this is for a coaxial cable, but it's the same as a cylindrical capacitor. So we'll do this and then also get a result for a spherical capacitor. And I think I've got a example problem involving a spherical capacitor. So see how that goes. The first question here is to use Gauss's law, good review of Gauss's law, to determine the electric field of a line of charge assumed infinite. And so just as a sketch here, I'll imagine this is a line of charge going infinitely far or a long ways in every direction. And it's got a charge per unit length lambda. So we'll have that. And then for Gauss's law, we make an imaginary surface here that takes advantage of the symmetry of the problem. So I'm going to make just a cylinder surrounding the line of charge that has a length L. And I'll use Gauss's law on that thing. And I'm just going to go really quickly through Gauss's law. Gauss's law is the integral over that Gaussian surface there of E dot dA. And there are three parts to this integral. There'd be the end caps, and then there'd be the curved surface. Now the end caps, the electric field will point radially away from the wire, which means that puts them in the plane of the end caps, but dA on those end caps points perpendicular to it. So E dot dA is 0 on the end caps. So I'm just going to ignore those because they're going to be 0, and I'll just have an integral over the curved part, the curved surface. And I'll just call it the integral over the curved of E dot dA. And we've done this a few times before now. E in this case is going to point radially away from the wire. So I'll just write it as E is equal to whatever the magnitude of E happens to be along some R hat direction that's pointing radially away from it. And then for dA, wherever I am on this curved surface, I'll just imagine a little chunk here, and dA will point radially away from that thing, and dA is going to be whatever its area happens to be in the same R hat direction. So if I take a dot product of this with this, I'll have R hat dot R hat. That's just 1. And so this integral over the curved part changes into just E dA. Maybe I'll abbreviate it the CP, the curved part, if you can still read that. And I can pull the electric field outside of the integral, and I'm going to bring it over here. E times the integral over the curved part of dA. Well, let's see. I'm going to be some distance r away from it while I'm doing this thing. And let's see, so 2 pi r times L is what the integral of dA is going to be. So I'll have E times 2 pi r L is going to equal the charge enclosed in my Gaussian surface divided by epsilon naught. Well, I enclosed a length of charge L, and it's got a charge per unit length lambda. So the charge enclosed is going to be lambda L. So lambda L over epsilon naught. And now I just have to solve for E. That was all I was after. Okay, well, if I divide, first of all, the L's will divide out. I'll end up with E is equal to lambda over, let's see, 2 pi r down there, or 2 pi epsilon naught r. And so that'll be my electric field strength. And drops off like 1 over r as you move away from here. Okay, now I'm supposed to use this result to determine the capacitance per unit length of a coaxial cable. A coaxial cable is one that, grab a piece of scratch paper here. Nowadays, in houses, most of the time you've got wireless connectivity, but used to be you had to connect these things coming in from an antenna or all kinds of different things. And sometimes you'd have to use them to connect like different, plug one into your TV that came from ancient VCR or something like that. But it's a cable that's got a central conductor down the middle of it. And then actually, if you look down the length of it, you'd have this center conductor. And then there'd usually be this is supposed to be all circles, like some kind of plastic or something like this. And then surrounding that would be a sheath of conductor. And a lot of times it'd be kind of braided copper that was surrounding this plastic. So more conductor. And then surrounding that would be a layer of insulation. And so you'd have conductor here, you'd have conductor here. And so these two conductors, you could have this one positively charged and this negatively charged. They actually had some capacitance. And at times, the capacitance of that coaxial cable could be a problem. I can remember some oscilloscope leads, and maybe today they probably still are like that, where they've got a center conductor surrounded by a layer of insulation of some sort, and then a conductor outside that. And for certain measurements, you might have to take into account the fact that your oscilloscope leads were had some capacitance to them. So anyway, that's a really bad drawing. Look it up online if you want to see a decent picture. All right, but now imagine that we have a center conductor here that's got a radius of, oh, I don't know, radius A, I guess. And then it's surrounded by, we'll just assume it's air between here, but then there's another part that has a radius that's larger than that, r sub b. And we'd have some sort of positive charge perhaps on the inner conductor, or you could have negative charge on the inner and positive on the outer. But let's just assume that we've got positive charge on the inner, and the electric field will have a strength of this between these two conductors here. And that will give rise to a potential difference here. And I can do another integral to figure out the potential difference between the inner and outer if there's a charge per unit length lambda that is on that inner conductor. So I'll just put an arrow here and say there's lambda on there, and we'll assume it's positive. If it's positive, the electric field points away from it in every direction, and the electric field points in the direction of decreasing electric potential, which means the inner conductor would be at a higher potential than the outer conductor, and we'd have a potential difference. And the potential difference between those two, which I can think of as V sub B minus V sub A, is going to be the negative of the integral of the electric field E dot dl. And I've used this expression a whole bunch since we started studying electric potential. Whoops, dl. L is a vector. Okay, well, the electric field, if I write it as a vector, something similar to what I did in part A is going to happen here. I'll have lambda over 2 pi epsilon naught. Got an R down there as well. And that's in the R hat direction. dl is going to equal dr in the R hat direction as well, because I'm just integrating on a straight line here. So it doesn't matter what path I take, but I'll just go straight line from the inner conductor to the outer one. And I should have had my limits on here. I'll have RA and RB for the limits of integration. But now, if I take a dot product of these two things, same thing happened as earlier. I'll have R hat dot R hat, which is 1, and the rest is going to be scalars. So my delta V, or VB minus VA, will equal the negative of the integral from RA to RB of lambda over 2 pi epsilon naught R. And I'm going to separate this times 1 over R. There's my electric field part. My dl part is just going to be dr. And this is constant, the lambda over 2 pi epsilon naught. So I can yank it out, and I'll have minus lambda over 2 pi epsilon naught R. Whoops, not R, didn't bring it out. The integral from RA to RB of dr over R. And you should know that's just the natural log of R evaluated at these 2 points, which will be natural log of RB minus natural log of RA, which is the natural log of RB over RA. So I'm going to do 3 calculus steps at once here, and I'll get VB minus VA is going to equal minus lambda over 2 pi epsilon naught natural log of RB over RA. And if lambda is positive, this is going to be negative, which just means that VB is at a lower potential than VA. And I haven't gotten to the capacitance part. If I'm interested in VA minus VB, which if I was hooking up a voltmeter, that's probably what I'd measure. It's just going to be the opposite of this. So lambda over 2 pi epsilon naught natural log of RB over RA. So that's the potential difference between 2 parts of a cylindrical capacitor. That's worth knowing about, I guess. Or between 2 parts of a coaxial cable, for that matter. It's going to be proportional to the charge per unit length on it, which isn't any big surprise. But now we need to figure out the capacitance of that thing. We know the potential difference, and the capacitance is going to be the charge you have on something divided by the potential difference. Okay, well, whoops, I should have had a Q on top. Okay, C for charge. No, it's C for capacitance, Q over delta V. Well, the charge on something like this would depend on its length, and that would be, let's just consider some chunk of the cable. The charge would be lambda times L, the charge per unit length, times the length of whatever it is that we have, and we divide by the delta V. So on the bottom, we'll have lambda, again, over 2 pi epsilon naught, and then I've got that natural log down there of RB over RA. Okay, well, let's see. The 2 pi epsilon naught's going to come up front, up top. The lambdas divide out, and I'll have 2 pi epsilon naught L divided by that natural log of RB over RA. So, okay, now that's the capacitance of some length. It actually asks for the capacitance per unit length. So I just divide by L. And capacitance for unit length of a coaxial cable is going to be 2 pi epsilon naught divided by that natural log. And so if you want more capacitance in your coaxial cable, you just double the length. So that's kind of easy to figure out. Okay, now we're not going to find any practical use for that capacitance in our class, but that's just something that you could do. Okay, one other problem here. Determine the capacitance of a spherical capacitor. So composed of 2 spherical conductors, one of radius R1 and the other of radius R2. This is going to be similar to what we had before, except now we've got spherical symmetry. When we have spherical symmetry, the electric field is always going to be, as a vector, it'll just be K sub E Q over R squared, and the direction will be in the R hat direction, radially away from the center of the sphere. And we could also write this as 1 over 4 pi epsilon naught Q over R squared in the R hat direction. So we can do that. But now we're going to imagine we're going to take some kind of a cutaway view here. This could be the center conductor of this case. And okay, I'm using R1 and R2. So R1 is the radius of the center sphere. And then R2, now remember, this is spheres and not cylinders. This will be R2. And I can calculate the potential difference between these things just like I did on the previous one, because for figuring out the capacitance, it's going to equal how much charge we have on something divided by the potential difference between the two parts. So I'm going to switch from a lowercase q to a capital Q for my amount of charge. And the potential difference, V of R2 minus V of R1 will equal the negative of the integral from R1 to R2 of E dot dl. I've already got an expression for E as a vector. dl is going to be pointing along the path I take from the surface of the inner conductor to the inside surface of the outer conductor. And I'm going to let it point along the R hat direction too. So dl will equal dr along R hat. Okay, well, just like I did before, when I take the dot product of this with this, the R hat dot R hat, the vector part, equals 1. And my integral will end up being, let's see, this is going to be V of R2 minus V of R1 will equal the negative of the integral of 1 over 4 pi epsilon naught. In fact, I'm going to change that to a capital Q and stick it on top of that. And then I'll have just dr over R squared. And my limits, R1 and R2, things are getting crowded. But this gets yanked outside the integral, and the only thing I'm integrating is dr over R squared. So minus Q over 4 pi epsilon naught and a minus 1 over r. When you integrate dr over r squared, or 1 over r squared, you get a minus 1 over r, evaluated at r1 and r2. And I can't remember where you're supposed to stick parentheses on those things, but if I reverse the order of the subtraction, I can change the sign on that to a plus sign. And so my V of R2 minus V of R1 will equal, let's see, oh, I should have moved it down farther. Oh, well, it'll be minus Q over 4 pi epsilon naught, and then 1 over R1 minus 1 over R2. Remember, R2 is bigger than R1, and we can simplify that expression to sort of simplify it. R2 minus R1 over R1, R2. And this, I did the same trick that I did back when we were studying optics, where we had, something, 1 over S plus 1 over S prime was equal to 1 over F. And sometimes I did that. All right. Well, I want Q divided by delta V. And by the way, this is V of R2 minus V of R1. If I decide that delta V for my capacitance expression is going to equal V of R1 minus V of R2, I just take this potential minus that potential. That will equal, I'll get a plus sign here, Q divided by 4 pi epsilon naught times that R2 minus R1 over R1, R2. Okay, capacitance, excuse me, is going to equal the amount of charge I've got divided by delta V. Well, I've got a delta V and I've got a charge there. If I solve for that in this expression, it's a little bit of algebra, but I'll end up with 4 pi epsilon naught times R1, R2 over R2 minus R1. And this is the capacitance of a spherical capacitor. So that's just kind of neat. Now we can start solving some other problems, because one of the problems we're going to solve involves a spherical capacitor. And let's see how those things can work out. Okay, this one is just looking at the energy in a charged capacitor. And we have a 450 microfarad capacitor charged to 295 volts. Then a wire is connected between the plates. How many joules of thermal energy are produced as the capacitor discharges if all of the energy that was stored goes into heating the wire? Well, here's what's going to happen. You've got this capacitor that's charged up, and it's got a potential difference across it of 295 volts, and that's what your voltmeter would read if you happen to connect it across there. And then you just take a wire and connect it from one side to the other. And so you've got the plus, 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 minus, minus, minus down here. And if you want to imagine the positive charge as the stuff that moves, you can think the positive charge, it's going to take the path of least resistance, which is through the wire, and it'll come over here and neutralize the negative charge. But as that positive charge goes through here, it's going to heat the wire up, and the stored energy that was in the capacitor is going to be dissipated as heat. heating up heating up the wire. So that's what will happen in this case. So how much energy is stored in a capacitor? That energy is 1/2 CV squared. Well, we know the capacitance. We know what the potential difference happens to be. This is the potential difference between the two plates. So just plug and chug here. 1/2, we've got 450 times 10 to the minus 6 farads. But let's see, capacitor is Q over V. It's a coulomb per volt is what we have. And then I'll be multiplying that by 295 volts squared. Okay. Volts squared here, volts squared there. Unit wise, I'm going to end up with coulomb volts, but a coulomb or a volt is a joule per coulomb, so it'll be coulombs times joules per coulomb. We're going to end up with joules, so that's good. I don't think we've done that before. And how much do I get? Not a huge number. Um, let's see. I think we only have two significant figures. So this would be 2.0 times 10 to the 1 joules. But on a skinny wire, that's enough to make it pretty hot. And you could possibly burn your fingers on a wire that, depending on how much wire you had, if it was just a short length of wire, it'd probably get pretty hot. So you could burn your fingers on it. Okay, let's try another. This is a long paragraph, but it boils down to not too bad a problem. Anyway, attempts to build a controlled thermonuclear fusion reactor, which, if successful, could provide the world with a vast supply of energy from heavy hydrogen and seawater. Heavy hydrogen would be the hydrogen that the atoms have a neutron in the nucleus as well as just a proton. So it's hydrogen 2 is another term for it. But to generate the currents, they have rooms full of capacitors used to store the charge necessary. One of the capacitor banks at Los Alamos Scientific Laboratory has capacitor banks of capacitance 61 millifarads this time. Usually they're not, they don't use millifarads, but in this case they do, but they're charged at 10 kilovolts. That's 10,000 volts. So that's quite a bit. So how much stored energy is in there? First in joules and then in kilowatt hours. Well, it's just going to be 1/2 CV squared. And so 1/2 times 61 times 10 to the minus third. Let's see, coulombs per volt. Again, that's what a farad is. 1 farad equals 1 coulomb per volt, just a reminder. And then I'm multiplying by 10 times 10 to the third volts, and I square that. When you square that, you're going to get 100 million volts squared. So this will be a little bit more energy. And see how much it happens to be. Um, Actually, it's either 3.0 or 3.1, but anyway, times 10 to the sixth joules. We figured out on the last problem that when you multiply coulombs per volt times volts squared, you get joules. So that's a fair amount. Now, how much is in a kilowatt hour? Okay, 1 kWh is equal to 1,000 joules per second. That's what a kilowatt is 1,000 joules per second times 3,600 seconds. This ends up being 3.6 times 10 to the sixth joules. So if we multiply that by 1 kWh over 3.6 times 10 to the sixth joules, you're going to get 5/6 of a kilowatt hour. So not so impressive, but it does have two significant figures. So that's 0.83, 0.83 kWh. Whoops, H is lowercase, I think, in that case. Actually, usually they just write it as all lowercase. But so not very much. And a kilowatt hour in, I don't know, Moses Lake is around 5 cents. So this would be about 4 cents worth of electricity, all for that. But actually, if you release all of that into a circuit at one time, you might be able to heat some stuff up pretty good. So, all right, lots of different energy problems here. Here's one that finally brings us back to the spherical capacitor. And it's two concentric spherical conducting shells separated by vacuum. So this is the spherical capacitor that we had before. And a couple things we figured out from that was the capacitance of a spherical capacitor was 4 pi epsilon naught R2 R1 over R2 minus R1. And also the potential difference in a spherical capacitor was, I have to bring myself back to that. It's equal to delta V. I don't know if we'll need this or not, but we might. Is equal to K sub EQ times R2 minus R1. Okay, and K sub E is 1 over 4 pi epsilon naught. So let's see what we need. So what's the potential difference between the two spheres? Oh, well, good. We do need this expression. And so for A, we'll just have K sub E is 8.99 times 10 to the ninth Newton meters squared per coulomb squared. That's the K sub E. How much charge do we have on here? 3.30 nanocoulombs. So 3.30 times 10 to the minus ninth coulombs. And then, let's see, inner sphere radius 10 centimeters. Separation between the spheres is 1.50. So that makes the outer one makes the outer one 11.5 centimeters. So R2 is 11.5. Oh, well, R2 minus R1 is 1.50 centimeters. Let's just write it that way. 1.50 centimeters. And then we divide by 10.0 centimeters times R1 is 11.5 centimeters. And I got that multiplication written in the wrong order. It should be R2, R1, but multiplication is commutative, so I don't have to worry about that. And that's the potential difference between them. How much we've got. Let's see, this will need to change units on this. Because this is going to be, yeah, I'll end up with centimeters on the bottom. If I multiply by 100 centimeters over 1 meter, yeah, I'll have to multiply the result of this by 100 in order to get meters on the bottom. Okay, well, I'll just multiply it by 100 before. And I have three significant figures. I get 38.7 volts. Oh, are they going to be volts? Better check that. I'll have Newton meters squared per coulomb squared times coulombs times 1 over meters. Okay, that 1 over meters makes that divide out. This makes that divide out. And I'll have Newton meters per coulomb, which are joules per coulomb, which are volts. So I do end up with volts. That's good. Then, what is the electric field energy stored in the capacitor? And is it the same at all points between the thing? Well, the electric field energy, U, is going to be 1/2 CV squared. I just figured out this, and it looks like I'm going to have to do a calculation here to get the capacitance. So we can do that. We know V, just figure that out. So the capacitance is going to be 4 times pi times, actually, I'm going to do this. I'm going to take 8.99 times 10 to the 9th Newton meters squared per coulomb squared. Oh, rats, running out of room. Try it down here. Now, what I just wrote is 1 over 4 pi epsilon naught. So I have to take this to the -1 and multiply it by the geometry terms here, which as I write them, I'm going to convert them into meters. So I'll have R2, which is 11.5 centimeters, 0.115 meters. R1 is 0.100 meters. And then on the bottom, I'll have R2 minus R1, which is 1.50 centimeters. So that's 0.0150 meters. Okay, what am I going to end up with units on this thing? It's going to be farads, I think, but I'll have Coulomb squared over Newton meters squared times, that's going to be meters squared over meters, which is just plain meters. So that divides out. I've got a joule on the bottom and a Coulomb squared on top. But remember, a farad is I'm going to take one of those coulombs and bring it down here. So a coulomb over a joule over a coulomb. Yeah, joule per coulomb is a volt. It's going to be coulombs per volts, and those are farads. So we're good to go. And I don't anticipate this being very big. Yeah, it's actually 8.53 times 10 to the minus 11th farads, which can also be written as 85.3 picofarads, which is one of the common ways of expressing capacitance. All right, well, finally I can figure out this energy here, and it's going to equal, oh, or did I just, no, I just figured out the capacitance. All right, I'll have 1/2 times that, which is 8.53 times 10 to the minus 11th. Farad is a coulomb per volt, again. And then I multiply that by the potential difference that I'm going to have, 38.7 volts squared. And that comes out joules, as we have checked before. So and I get not much. 6.39 times 10 to the minus 8th joules. So pretty dinky. This isn't a very efficient way to make a capacitor, apparently, and to store energy in it. Now, it asks, is the electric field energy the same at all points between the shells? And it's not. And that's because electric field energy stored in an electric field is 1/2 epsilon naught times E squared, where E is the strength of the electric field. And you could actually integrate this to figure out how much energy. Oh, wait, this is a lowercase u. This is the energy per unit volume. You could actually integrate this, but the electric field in this case, in between those two shells, is going to be K sub B times the amount of charge you have on that thing, the 3.30 nanocoulombs, divided by R squared. And that's the magnitude of the electric field. So it's diminishing constantly as you go toward the outer conductor of this spherical capacitor. So on what I could have you do, or what happens in one of the homework problems, is you're supposed to calculate this for a cylindrical capacitor, if I remember right. And you'd have to integrate 1/2 epsilon naught E squared and over the volume as you go from the inner radius, the R1, out to the R2. And so the 1/2 epsilon naught can come outside the integral. E is K sub B Q, that can come out also. Well, I'll go ahead and write all the parts out here, but integral from R1 to R2 and 1/2 epsilon naught times K sub B squared Q squared over R to the 4th. Now that's just taking care of the electric field. dV is going to be, let's see, a spherical element unit volume. I can write it as 4 pi r squared. That's the surface area of a sphere, and I multiply it by dr, a little tiny thickness. And this would be the volume of a thin spherical shell, that thin, dr, that is at whatever radius we're considering at this time. So when you pull all the constants out that you can, you'd have 1/2 epsilon naught k sub e squared q squared, and then, oops, and a 4 pi as well. Oh, actually, we've got a 4 pi epsilon naught here, which is 1 over k sub e, so we'll end up with a single k sub e. That's good. So that's all the constants I could pull out of here. And left inside, integrating from R1 to R2, I'll have an R squared over an R to the fourth. I'll actually have dr over R squared. And if you integrate that with the numbers we've got in this problem, you should end up with, shoot, we've got time to do it. Let's go ahead and see what happens when we integrate it here. And let's see, I'm gonna look at it here first. I'll have, simplify it a bit, 1/2 times 4 pi epsilon naught times k sub e squared, which is actually 1 over 4 pi epsilon naught squared, just making sure I take care of everything, and then q squared. And then I will be integrating from R1 to R2, which is, let's see, 0.100 meters to 0.115 meters, and dr over r squared. So, okay, now I can plug all the numbers in, and we'll see if this actually works. I'll have 1/2, and then I'll have 1 over 4 pi epsilon naught. Q, I figured out, was, they gave me that 3.30 times 10 to the minus 9th coulombs squared. Oh, yeah, and I actually haven't put units on this yet. And then minus 1 over r, which I'm evaluating at 0.100 meters and 0.115 meters. Okay. We'll see if this works out. 1/2, 1 over 4 pi epsilon naught is 8.89, no, 8.99 times 10 to the 9th Newton meters squared per coulomb squared. And when I square that, well, I'll just square it later. But that's going to be coulombs squared, so the coulombs are going to go away. And then I'll have, if I reverse the order of the subtraction, I can change that to a plus sign, and I'll have 1 over 0.100 meters minus 1 over 0.115 meters. This is complicated. Equals, now I can plug in all the numbers. We'll see what we get. Oh, I had to square this, forgot. times. I get, this time, I only get 6.38 times 10 to the minus eighth joules. Before I had 6.39 times 10 to the minus eighth joules. So got a little bit of round off error. There's uncertainty in this last digit. But anyway, it came out the same way. But this was a whole lot more work to figure out um, to be able to do this. But you can do it that way. So you can either use 1/2 C delta V squared if you know C and delta V, or you can integrate the electric field energy density and get it that way. So you get the same expression either way. All right, I think that was almost the last problem. Oh, there was one more. And this is kind of a simple little kind of sort of. Anyway, the first thing you're supposed to do is determine the equivalent capacitance of the group of capacitors below. So what you've got is a wire comes down here. There's a split and two branches. This branch has a single capacitor. This branch has two capacitors in series. And so we need to remind ourselves in series, the equivalent capacitance 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So, and we actually have to figure that out first, is this combination. And then we'll have two capacitors in parallel. And so as we go through these steps on this thing, we'll have an equivalent capacitor for those two parallel ones. And then we've still got the 2.5 microfarad capacitor here. And we'll have these two in parallel, but in parallel, it's easier. C equivalent is just going to equal C1 plus C2. Okay, now that's this C equivalent is not the same as that C. Maybe I should call it C3 or something like that is equal to C equivalent plus C2. Okay, but the first thing we need to do is figure that thing out. And when I just have two capacitors involved in this thing, I can write this as C2 plus C1 over C1 C2. And actually C equivalent for just two capacitors will equal C1 C2 over C1 plus C2. So you can convince yourself of that if you play around with this. Get a common denominator, add them together. Then you'll have a simple fraction. Reciprocals of simple fractions equal that. So that's what it'll equal. Anyway, so this will C equivalent for this first part. The equivalent capacitance of these two will be 0.30 microfarads times 10 microfarads. And I have no idea how many sig figs we have on this. Since we've got two here and two here, let's pretend that's 2. And then C1 plus 2, C2 would be 10.30 microfarads. And I know I'm fudging, but I'll round the result to the correct number. Okay, I get an equivalent capacitance here of 0.29 microfarads. So now I'd have a 0.29 in parallel with that thing. And coming down here, I would have just, well, 0.29 microfarads. I just add these two together, and that actually gives me 2.8 microfarads. So, and this could be my C3, 2.8 microfarads, just adding this to that. Okay, so that was part A, and actually, the book I took this out of was the open source or the OpenStax book. That's all you had to do on it. But I was wondering, suppose you hooked a 14.5 volt battery connected across this group of capacitors. And so kind of imagine what we're doing here now. So, I don't know that you can buy a 14.5 volt battery, but you could do it with a power supply. So anyway, now we have this 0.30 microfarad in series with a 10 microfarad. And so we've got a 2.5 microfarad. So here's our circuit. We've got a battery in there. And I'm supposed to figure out the potential difference across each capacitor, as well as the charge on each capacitor and the energy stored in each capacitor. Well, this is a lot of work. However, if I can get the potential difference, I can actually find the energy stored in each capacitor, and then actually, if I know the potential difference, I can get the charge easily too, because some of my relationships for capacitance are that the capacitance is equal to the charge on it divided by the potential difference across it. So when we figure out these potential differences, we can easily figure out the charge and then figure out the other stuff. Well, one of these is going to be easy. The 2.5 microfarad capacitor, it's going to have a 14.5 volt potential difference across it. Because if you connect a voltmeter here, you get 14.5 volts. If you connect a voltmeter across here, you get 0 volts because there's no change in potential when you're going down a wire. And so to find, you could stick a voltmeter here and get 14.5 volts. You could also stick it here and get 14.5 volts. You could stick it here and get 14.5 volts. Now, that tells us the potential difference across this capacitor, but it won't tell us the potential difference across these two. We have to do a little bit of work to figure that out. But I think we can probably do that. Okay, but anyway, for the 2.5 volt or microfarad capacitor, cap, I'll just say delta V is going to equal 14.5 volts. Right? Well, delta V is equal to Q divided by the potential difference. The charge will equal just the capacitance times that delta V, C delta V. So I can just multiply this by 14.5 volts. It's not going to be a lot of charge, but 14.5 volts times 2.5 microcoulombs, or microfarads, and a farad is a coulomb per volt. So I get 3.6 times 10 to the minus fifth coulombs for the charge on that one. And the energy that's stored in that one will just equal 1/2 C times that delta V squared. So with 5 times. Okay, took longer than it should have. I get 2.6 times 10 to the minus fourth joules for that capacitor. Now, for these other ones, I need to do a little bit more reasoning on this. Here's what I've got. I have these two capacitors in series. I've got the 0.30 microfarad. Yeah, that's the one on top. And the 10 microfarad. And I have a 14.5 volt potential difference across them. Okay, so then I'll just imagine that I've got a voltmeter there measuring that. Okay, well, what do I know? I know that if I call this C1 and this thing C2, I know that delta V for that capacitor plus delta V for the second capacitor, C2, will equal the 14.5 volts. So I know that. I know that they're both going to have the same charge on them because capacitors in series get the same charge. So Q1 will equal Q2. And let's see, what else can I write down here? The capacitance C1 will equal Q over delta V1, and C2 will equal the same Q over delta V2. So what can I do with that? I think I can, let's see, well, delta V1 will equal Q over C1. Delta V2 will equal Q over C2. Yeah, I've got enough to solve this now, except I'm out of time. Anyway, this isn't a horrible problem. It's just time consuming. So I asked too many things in it. But what I can do is delta V1 plus delta V2 is 14.5 volts. So I know Q over C1 plus Q over C2 is 14.5 volts. That will let me figure out what Q is. And then once I know Q, I can figure out the potential difference across each one of these things. So, all right, just a little more work. So we'll stop there and continue on with this stuff tomorrow. So I'll stop recording there.